transitions. First of three lectures.
So, first of all, I naturally thank the organizers for putting together this beautiful meeting at this even more beautiful place. Second, I would like to thank you all for staying at this late hour, despite the beach being out. So this is the first of three lectures on orbital selective Mott phases and orbital selective Mott transitions. And I want to call this a new paradigm. I'm not sure whether it will really turn out to be one, but you may judge in a few days from now. So as far as my own work is concerned, it has been done together with a few people which are now distributed over various places in the world. And there are some funding sources which need to be acknowledged. So before I give you an overview of what I want to cover in these three lectures, let me just briefly briefly walk you to the final goal, namely what this orbital selective Mott phase is, which I want to talk about. So the first obvious question, what is a Mott insulator? This has already been covered in more than one talk today, so you have probably even seen this or a very similar picture. So we are talking about fermions, subject to local Coulomb repulsion as in the Hubbard model, and then at half filling, and in the limit of large U, the statement is that particles get localized to the interactions, which is supposed to be shown in this picture. So this shows the periodic potential. One particle per site, exactly one particle per site, so the particles don't move anymore, because if they would move, they would have to pay U, and that's a Mott insulator. Now, among interesting characteristics is that this phase has a gap to charge excitation, so it means there's a finite amount of energy which you have to pay if you want to either let a particle hop from one side to the other, or to remove or add the charge. So it's not a metal, so it doesn't have a Fermi surface, and for fermions, and that's the interesting difference to bosons, there are now residual degrees of magnitude of freedom, which are the spins. And those essentially are at the heart of all the interesting physics of Mott insulators. Now, if we discuss Mott insulators, then we have to actually say what those spins are doing at low temperatures. And there are various possibilities, and I've listed here three, among probably a few more, together with a few compounds where this is realized. So what you see here are phase diagrams of those compounds, temperature and pressure on the horizontal axis. And I will discuss them actually in turn over the course of these lectures. But let me just here briefly state, so what you see here, for instance, this material V203 is a phase diagram where we have an antiphrenetic insulating phase at low temperatures, but at elevated temperatures you have the first order transition between a metal and an insulator, and this is apparently something which we are going to talk about, because this is supposed to be a Mott transition. And similar things happen in these two organic materials where the phase diagrams are shown here. So you have various types of insulators, you have a metal and you have a superconductor here. And for this slide, I only want to focus on the type of magnetism which emerges in the insulating state. And so over here, this is a simple antiferromagnet with this cartoon picture. So spins are simply antiparallel on some bipartite regular lattice. Over here, the so-called valence bond solid forms, which can be understood by saying that spins form pairwise singlets. So a cartoon picture like this, where now these red strong bonds are supposed to be singlets made out of two spins 1/2. But this is the dominant component in the wave function, and this is now paramagnetic Mott insulator at low temperatures. Whereas here, supposedly, something more exotic happens, namely a spin liquid, which in short is a state which does not break any symmetry, neither the spin symmetry nor the lattice symmetry, despite actually having one spin 1/2 per unit cell. And since I don't have a good picture for a spin liquid, I just this. And this also will reappear in the course of the talk. Now, what is an orbital selective Mott phase? This is eventually what I'm driving at. And so this is now something where we have to talk about more than one band. Notice so far I was talking about one band physics, but this is a school about multi-band and multi-orbital effects, so here they are. So we talk about a system which has at least two low energy bands, so low energy means that they potentially cross the Fermi level. We are in a situation where one band, at least one band, is metallic, and the other band is half filled and Mott insulating. So I will argue that such a situation can exist. And then in this one half-filled and one insulating band, we have local moments. And this will be the interesting phase. And it will be particularly interesting if we are in the absence of broken symmetries, so in such a spin liquid, which I was just advocating before. And then if the number of bands where this particular Mott phenomenon, and this is now an orbital or band-selective Mott phenomenon, occurs where the number of these bands is odd, then again we have a half integer number of spins per unit cell. And then I will argue, and this is what I will be driving at actually in the second lecture, that here we have a very interesting phase where conduction electrons, namely this metallic band, coexist with this exotic spin liquid. And this is one of the prime examples of a true non-Fermi liquid phase of higher dimensions. So if we think about non-Fermi liquid phases, this is something rather elusive. We know it happens in interacting 1D electron systems where we have Lagrange liquids. But in dimensions 2 or larger, we have actually very little theoretically established examples of non-Fermi liquids. And I will argue that this is one which deserves more attention. And probably is also realized in a few compounds, and I will talk about explicit experimental examples actually in the third lecture. So here is now what I want to cover. So today, or I should say tonight, I will only do simple stuff, namely Mott transition in one-band systems. And in particular, I will explain in somewhat more detail what is interesting in these spin liquids, which will reappear then in the second lecture, where I will introduce the concepts of this orbital selective Mott transition. I will actually connect this to another piece of physics in the heavy fermion world, where this has been dubbed the quantum breakdown transition. And I will actually argue that the two are qualitatively the same thing. And I will also support this with some microscopic considerations. And then in the third lecture, I will come to a few examples, which include a few heavy fermion compounds, some of the iron arsenides, iron nucleotides, those things. And I will actually also talk about cuprates, because I think they might be a very interesting example of a very similar phenomenon. Okay, so let's talk about Mott transitions. And some of the stuff you already heard in the previous talks where Mott insulators were discussed, but I will now particularly focus on the transition. So we talk about a metal insulator transition, and then we can ask a few conceptual questions. So apparently when we talk about metals and insulators, then a sharp distinction can be only drawn at t equals 0, and the distinction would be that the conductivity is either finite or 0, where of course finite should be infinite in the absence of impurities. So you could say the Drude weight is either finite or 0, finite in the metal, 0 in the insulator. Then of course you from this discussion you might then ask that whether the concept of this transition is only well defined at t equals 0. And in some sense this is true, but as you have already seen in the experimental examples, there is the possibility for first order metal insulator transitions at finite temperatures. And then of course this will be a transition between a phase which has a finite small conductivity to a phase which has a finite large conductivity. So according to this criterion, the phases are not distinct, but if the transition is sharp in first order, then of course it still makes sense to talk about metal and insulator in this context. Now, if we talk about these two phases, then one obvious question is what happens to the Fermi surface right at the transition, and what happens to the associated low-energy quasi-particles. And then, of course, the question, is there anything interesting regarding the critical behavior? And a similarly fundamental question is magnetism relevant for this transition? You have seen that magnetism is relevant to describe the nature of the insulator, and then of course this is a very natural question to ask. I will not be able to answer all these questions, but I will at least try to discuss them. So let's first look at experiments again, before coming to a more theoretical discussion. So this was the phase diagram of V203, which you have already seen a few slides ago. This is just the same thing, somewhat enlarged. So here is temperature, here is pressure, and what you can see is that there is this antibiotic insulator at low temperatures, which dominates essentially all the low temperature physics, but there is this finite, this transition line at finite temperatures, which is a first order transition between metal and insulator, and this ends in a critical endpoint. And again, if you cross this transition line here, then you have a jump in the resistivity from some small value to some large value, and the magnitude of this jump decreases until it vanishes right at this critical point, where one in principle gets critical behavior associated with power law singularities. I will not discuss this in more detail here, because at some point, of course, I'm heading for multi-band physics. But this critical endpoint is a rather interesting point to discuss. Let's just look further among the experimental examples. This is another of the organic materials. This is actually a system which lives on a triangular lattice, which has this complicated structure. And here is a phase diagram, temperature versus pressure again. And here you see a variety of phases. Let me just first point out there is also an antiphonetic insulator here at lowest temperatures on the insulating side at low pressure. There's a seemingly ordinary Fermi liquid at large pressures. And there is a coexistence region in between here, again associated with the first order transition, which is here right in the middle of this coexistence region, which again ends at a critical endpoint, which has been located somewhere there. And here are a few crossover lines up there, and on this side here it makes sense to talk about a non-magnetic Mott insulator in the same sense as in the previous phase diagram. This phase here you could call a non-magnetic Mott insulator, because again, if you cross this line, the resistivity jumps by a large amount and is much larger here on the insulating side. So this is qualitatively similar to the previous example. Now, there are two other examples which you also saw a few slides ago, and here are again the enlarged versions, temperature, pressure in these two organic materials. Here, the situation is different because here, as I already said, the insulator is not magnetic. Here you have this valence 1 solid phase, again schematically depicted here. And there is actually a first order transition to a superconducting phase. And also a first order transition to a metallic phase at elevated temperatures. Note that this temperature scale here is logarithmic, but this enlarges the low temperature features. But there is also a critical endpoint here, and there is also a Mott insulating phase which doesn't break any symmetries here at elevated temperatures. Here in this compound, it is believed that there is no symmetry breaking whatsoever on this low pressure side. So in other words, here there could be a spin liquid Mott insulator, which again, upon pressurizing, gives way to a superconducting phase. And I guess this transition is first order, but I'm not absolutely sure. Perhaps there are some experts here who know that. Doesn't matter for the remainder of the discussion. And again, there's a metallic Fermi liquid phase out here. So there seems to be a variety of Mott transitions occurring in experimental systems. And so Mott transition apparently would be the transition which is driven here by pressure. So I mean, the interesting Mott transition, let's say occurring at 0 temperature, which is driven by pressure moving along this axis. And apparently there is here, these compounds, a superconducting phase intervening. There's another example of a different type of Mott transition, namely a Mott transition driven by doping. And I've just took one very popular example, namely cuprates. So this is the cuprate phase diagram, which you have all seen many times, temperature and doping here. And the Mott insulator now resides on this axis, which is the half-filled limit. And then interesting physics happens upon doping of this Mott insulator, and among others, there is superconductivity. So I will come back to this actually in the third lecture where I discuss cuprates.
Just for completeness,
yes.
I could say that there is a very, very similar case, which is the case of fullerenes, cesium 360, in which we have a very nice Mott transition with pressure to a superconducting state. It's not that much, you know it maybe, but
true.
It's not that known so far, but I'll give a talk on that next time.
This overview here is by no means inclusive, of course.
No, but there are not many others. So,
true. So you are saying I only left out a few. I'm sorry for that.
Matthias,
yes.
Where would the Mott transition be on that phase diagram? Exactly where?
You know that this is a philosophical question. Well, I believe that if we would look at the Hubbard model, the plain Hubbard model, no long-range interactions involved, then the system should be, and no disorder involved as well, then the system should be conducting and hence metallic and infinitesimal doping. In this sense, the Mott transition happens once you depart from half-fill. And the fact that this is not realized
If it doesn't have sufficiently strong long-range magnetic order, where it could be insulating even in the doped system, right? In principle, at least.
But you can.
Well, I mean, of course, we should have to distinguish whether antiferromagnetism. Suppose there is antiferromagnetism half filling, then we have to discuss whether antiferromagnetism survives finite doping, which usually it does. But nevertheless, even if it does, I would suspect that this doped antiferromagnet should be metallic, because there are charges which are in principle free to move, and we know that there is a reduced bandwidth due to spin fluctuation effects, blah blah blah, spin Polaroid physics. But in the absence of disorder, in the absence of long-range interactions, I would expect this thing to be metallic.
Okay.
Now, of course, with long-range interactions, you first get a Wigner crystal, and with disorder, things get even more complicated. Then you get this. But I think on clean theoretical grounds, there's only a Mott insulator strictly at half filling.
Lower left corner then.
Well, I mean,
true.
So the strict insulator, as I said, is only there at zero temperature. So this is the Mott insulating point, and everything else is.
Just to set this finite rule away, that not zero dose. There's finite rule away, right? So then it becomes your definition.
But DC conductivity is, I mean, it goes up, but the DC the resistivity goes up. So this is certainly, I mean, if you are a very small doping, 1%, and you ask experimentalists, they wouldn't call this a metal. So you see variable.
Is there a finite rule away?
You see variable range hopping in the resistivity, which qualifies as a very nice insulator.
But you always have disorder.
Right. This is exactly, well, I mean, you can't blame the compounds. I mean, this is how nature works. Anyway, so now let's go a bit more theoretical. So this is the Hubbard model, which you have already seen. So we have kinetic energy, and we have this Hubbard U, and the cartoon picture is shown here. The cartoon picture close to half filling. So it's important to notice that most of the discussion which comes in the next minutes is actually at half filling. So if we are close to half filling, then we have almost everywhere we have 1 electron per site. If this U is not small, then essentially there are these processes where you can generate double occupancies. And then if you are away from half filling, then of course, like in this picture, you have less electrons than lattice sites, and then there's a possibility for holes actually to move, or equivalently for electrons which are neighboring sites to holes to move. But that is what the model describes. And now we expect, as I said, that for small u we have a metal in this model, because small u should be conservatively connected to 0 u, so there should be a metal. On the contrary, for large u we expect this Mott insulator. And what I want to discuss now is how the single particle spectrum is expected to look like in the two phases, and then how this supposedly changes across the transition. So I will draw pictures now for the momentum integrated density of states, which is an easy thing to discuss. And so for the uncorrelated metal, there is just some finite density of states near the Fermi level, and this here is just reflecting the shape of the uncorrelated band. This may, of course, look different depending on the lattice, which we are moving on, but qualitatively it's something like this. So now if we go to the large U limit, then again things are relatively easy to discuss, because at the large U limit, you can imagine first setting T to 0, so this is the atomic limit. And then we can actually calculate how the spectral function looks like. And the equation is here. We get two peaks, one at minus U over 2 and one at plus U over 2. And this is schematically depicted here, so frequency and spectral density. We get two peaks, one minus U over 2, one plus U over 2, which are split by a large gap, which in the atomic limit is simply U. And usually these bands are called Hubbard bands, and then this here is what should be the spectral function in the Mott insulator. Notice that this picture here doesn't know anything about spin degrees of freedom. I mean, that's apparently too simple. The spin degrees of freedom will play a role at low energies, but what I'm discussing here is single particle excitation, and as I said, there is a large gap to single particle excitations in the Mott insulator. Now, the apparent question is how you go from here to here upon increasing U, because this is what the Mott transition is about. So the questions to ask are then essentially, Why does the remote not work? This is one question. Let me see whether I can make it work again. So the questions to ask are, again, what happens at low energies when you approach this critical value, which I've just labeled UC here, and then you can try to ask questions like, what happens to the quasi-particle weight? Of course, this metallic states here near the Fermi level have some quasi-particle weight. Does it go to zero if you approach the Mott transition? Alternatively, or even equivalently in a local approximation, does the effective mass diverge? Or you could also ask, does this gap here go to zero if you approach the Mott transition from the insulating side? All these are apparently valid questions, and we need a theory to address that. And there have been various attempts to address those questions in the early days when the Hubbard model was proposed, and they were in some sense all not very satisfactory. And there was some development in the late 80s, early 90s, which is called dynamical weak field theory, which provides a partial answer to these questions. And I want to give you now an overview of what dynamical weak field theory is and what comes out for the Mott transition in, let's say, 10 minutes, which of course is much too short, but I guess you will get the important points. So what is dynamical weak field theory about? Dynamical weak field theory starts essentially from the observation that the dominant correlation effects in the Hubbard model are local in space, because essentially you have this local Coulomb repulsion, and this is also what actually immobilizes the electrons in the Mott insulator. And then if the correlation effects are local, then it makes sense to disregard the spatial dependence of the electronic self-energy. So self-energy now arising from the Hubbard U, and then to approximate the self-energy, which is a momentum-dependent function, frequency-dependent function, by a function which only depends on frequency. This approximation can be justified in some limit of large dimension, but this is not what I will want to discuss here. I will just consider this as an approximation to a real system in finite dimensions. And then, if we do this, then it turns out that we only have to solve a local problem, because essentially we have disregarded the spatial dependence of the self-energy. And one can show that the lattice model, like a Hubbard model, maps onto a quantum impurity model supplemented by some self-consistency equation. This is essentially what the DMFT machinery does. And so the result is that we have to solve this quantum impurity model in order to understand the physics of the Hubbard model. So there are a few more equations here, and I will not discuss these in any detail. This is essentially the formulas describing what I just said in words. And so what you then have to do, and these four people are, I guess, the ones which have in the 90s most extensively worked on that. What you then have to do in DMFT is you have to solve an impurity problem. The central object, there is an iteration cycle, which is schematically shown here. The central object in this iteration cycle is now the self-energy, which is a function of frequency. That's why it's called dynamical weak field theory, because you're still keeping the full frequency dependence of your interaction effects, such the full frequency dependence of the self-energy. And so you can read this actually this way around or this way around, depending on how you like it. But so the central thing is that there is a local Green's function which essentially defines your impurity problem, and if you solve this impurity problem, you get a self-energy, and from this self-energy, together with a certain form of lattice, so this here is supposed to be a summation over k or over energy, with a certain lattice, you then recalculate the local Green's function, and then which defines again a new impurity problem, and then you iterate this loop until self-consistency. So there are essentially two steps. One is the solution of an impurity problem, which brings you from here to here, and there's another step where the structure of the lattice on which you work enters, which then translates this self-energy, which you get from the impurity problem, back into a Green's function, which describes the effective bar. Again, all this can be done and discussed in somewhat more detail, but this is not what I would want to do now. But I would only describe results which come out from this procedure for the Mott transition. So, if I want to do that, I first need to discuss the conduit effect. And I will again do this in like 2 slides. And I need to do this because we just learned that we have to solve an impurity problem. So what we will have to solve is the physics of a magnetic moment immersed in a bath of conduction electrons. So why this is so? Because we have learned essentially that in the Mott insulator there will be local moments forming. And then the Mott transition is apparently about describing the fate of these local moments upon letting them interact with conduction electrons. And this is the Kondo problem. So we are now discussing the physics of one spin moment coupled to a conduction C. So this is not a very nice cartoon, but it shows the relevant physics. And this is described by, for instance, this type of Hamiltonian, and I need to spend a few words on this. So this is what is usually called the endless impurity model. We have conduction electrons here with some dispersion. And then we have impurity electrons, which are labeled by these D operators. And so there is a level energy D for this one D level. There is a Coulomb repulsion in the very same spirit as the Coulomb repulsion Hubbard model. And then there is a hybridization which lets electrons hop from the conduction band to this impurity orbital. And the physics of this model can be understood by first switching off this coupling here and just considering the isolated impurity level. And if you assume that the energy of this level is negative, but U is large and positive, then the lowest energy state of the isolated impurity will be a singly occupied state. But this is how a local moment forms in this description. And so the statement is, again, if U is large and epsilon D is negative and also large, then there is a local moment forming. If you imagine you cool down, then the local moment forms at temperatures of order U. Because this is when this impurity essentially locks into a singly occupied state. So in other words, you go from 4 relevant states in the Hilbert space, which this one electron level has, to just 2, and then you spin up and down. And then you can ask, what is the physics of this local moment at low temperatures? And this is the question where the Kondo model comes into play, which now describes conduction electrons only coupled to a spin. What this term here is an exchange interaction between the spin and the conduction electron spin density. And this is supposed to be a low energy model for this Anderson model in precisely this limit where U and epsilon D are large and epsilon D is negative, because this describes the fate of the remaining 2 states in the Hilbert space if you couple them to conduction electrons. And now if you analyze this model, which I have no time to do at any length here, and you ask the question, what is the fate of this local moment in the 0 temperature limit? Then the answer is, this moment will be streamed. In other words, there is a collective many-body singlet forming between this spin and the conduction electrons. This happens below a characteristic temperature, which depends exponentially on the input parameters. Okay? So this is all well understood. Now you can ask, what is this, how does this screening show up in the electronic spectrum? After all, we are discussing Mott physics, and we want to understand how the single particle spectrum looks like in the vicinity of the Mott transition. And the statement is that, and these are now pictures from real numerical calculations for such an Anderson model. This is actually taken from Houston's book. The statement is that if you are at very small u, this curve should be colored, I apologize for the mess here. So if you are very small u, you just get a peak at the Fermi level. So this is actually the model here in the absence of interactions, which you would call resonant level model. But there's nothing interesting happening. You just get a metallic peak at the Fermi level. But if you go to large u, then you get a characteristic structure which contains 3 peaks. So this is, for instance, if you focus on this curve here at u equals 6, where we have 1 peak here and 1 peak here, and then a very narrow peak at the Fermi level. And the idea is that these 2 peaks here are essentially like the atomic limit peaks I just described when discussing the Hubbard model, actually in the large U limit. So these you might call, so the Anderson model you would call these the peaks corresponding to charge excitation. And then in the middle you get a quantum resonance, and this is the signature of screening, and the width is actually given by this exponentially small quantum scale. Okay, now we need this actually in order to understand what happens when we discuss DMFT for the single band Hubbard model. And so let me first flash the phase diagram which comes out of DMFT, now performed for the single band Hubbard model at half filling. And so the qualitative phase diagram, actually it's quantitative, there are numbers here, is shown here. So here is temperature, here is U. And so at small u there is a metal, at large u there is an insulator, so no surprise here. There is a first order transition in between, which ends in this critical endpoint. And these dashed lines here actually bound the coexistence region between the 2 phases. So if you now look at the spectral functions, then at small u, you get essentially this one peak near the thermal level corresponding to the uncorrelated band. This is again spectral function momentum integrated versus frequency, and the chemical potential is supposed to be in the middle. At large u, you get this two-peak structure, which I was advertising in the atomic limit. So you get two Hubbard bands and no signal at the Fermi level. So this is clearly the insulator. Whereas if you are close to the Mott transition, on the metallic side, you get a structure which looks like this. And the most important thing is there is a very narrow peak here, right at the Fermi level. And there are these two bands, and the shape of these bands actually depends on which approximation you use to solve the DMFT problem. There are two peaks here at finite energies. And so apparently these here are now your Hubbard bands, which become these two bands if you go into the insulating phase. And the Mott transition is about the disappearance of this narrow band at the Fermi level upon crossing this phase boundary. So this is what DMFT shows.
So I wonder, so when you do this clustering theory, so this first order transition becomes continuous or stays stationary?
So you're right in pointing out that I'm discussing single-side DMFT here. And cluster DMFT, the discussion gets much more complicated. Actually, then you have to say on which lattice you are working, and you have to say which clusters you are using, and there is no universal picture has emerged as of yet.
So I thought the cluster DMFT, this small peak in the middle, normally disappears. Isn't that what you're getting at?
Well, I guess this is not true in general. So I mean, if you are in this regime here where you would call the phase a correlated metal, I guess the results of the cluster DMFT are qualitatively similar to that. So you get Hubbard bands and you get a Fermi liquid peak in the middle. So this does not change qualitatively.
Now, another question I have that what I learned in school, that you have the sum rule that always tells you there's this delta function right in the middle, right?
Sum rule also you see here in this picture because all these peaks have the same height. So that is that is a result of Friedel sum rule, indeed. Yes.
So that why does it then disappear at the right down side where you have this bands completely separate to the right of this picture?
So what? Okay, so that's exactly now we have to discuss how we go from here to here. And first, of course, we can discuss how we go from here to here. And there, what you point out is that the height of this peak here, plotted in reasonable units, is always the same. So this is fixed by Friedel's sum rule. I have 5 minutes left. Okay. And so the height of this peak doesn't change. What changes is the width. And so approaching this phase transition line, the weight of this thing goes to 0. But the height stays constant. And then what happens when you approach this particular point, which is labeled UC2, then the weight becomes 0. But this happens actually in the presence of this preformed gap. And then this is the way how you go from here to here. Again, you just have to imagine that this peak here continuously shrinks in width and then disappears at this critical level of UC. So, and that means that this transition has both first order and second order characteristics. It's second order because this weight disappears continuously, but it's first order because the gap doesn't close when you approach this UC2 point from above. The gap actually only closes at UC1, but this is not a stable thing. Now, this all looks nice, but we have to remember that this is DMFT, and DMFT has a number of drawbacks, and in particular, all non-local correlation effects are missing. That means there are no correlated fluctuations of spins on neighboring sites, which in particular implies that this Mott insulator here has free spins, so there's a residual entropy of log 2 per site. That's of course not a stable phase of matter. And a real Mott insulator will resolve this problem by either realizing magnetic order or the spin liquid, which I already advertised. So in magnetic order, these spins would be simply polarized, and in the spin liquid, they would stream themselves by non-local correlation effects. So all this is not included in this description. And so the conclusion is that in some sense this picture can only be valid at elevated temperatures. And so from this consideration you would conclude that the generic phase diagram looks somewhat like this. So that's essentially the same phase diagram as before, now where by hand one has added an ordered phase because we know that the spins have to do something at low temperatures. But the story would be that possibly this first order transition line sticks out of this ordered phase, and then this piece of this Mott transition line, including the critical endpoint, might be visible. And indeed, we know that this is what happens in this particular material. It happens in B203, but in this one, physics is apparently different. Okay, so if we confront this with experiments, then we can say that it's not so bad. We have succeeded with something because we have succeeded in at least qualitatively describing this finite temperature first order transition between a Fermi liquid and paramagnetic Mott insulator, where the spins are essentially free. And this seems to apply to a number of materials, but we also have to conclude that we have learned little about low temperature, because at low temperatures DFFT is not very powerful. Okay, now this brings me to a discussion of what the low temperature physics of these spins actually could look like, and this will be the last few slides which I'm going to show. Namely, I already advertised that there can be magnetic order in this Mott insulating phase, which is in some sense trivial. There can also be this valence bond solid formation, but there can also be spin liquids. Now, how do we have to think about these spin liquids? Well, this is one way, this is the beach way. But let's put this discussion on somewhat more clear ground. So suppose we start with a concrete model of an antiferromagnetic Mott insulator, and suppose we actually now only keep spin degrees of freedom, and I'm doing this here on a regular square lattice, and suppose I have a Heisenberg model to begin with, and we have learned today that the Heisenberg model, of course, is a good low energy model for the spin degrees of freedom in such a Mott insulator, then this is the ground state. Now, what can we do to disrupt this? We can add terms which counteract this magnetic ordering tendency. And one way which has been proposed is to add a ring exchange term, which pictorially does what these green arrows are supposed to show. Namely, they rotate spins clockwise and counterclockwise along one plaquette. So if you imagine acting with such a ring exchange term on a plaquette here, then all the spins along one square would be reversed, so this apparently counteracts magnetic ordering tendencies. So the idea is, if you now vary the ratio of J and K, then if you make K large enough, you can destroy magnetic order. And indeed, this is what happens as shown in this particular paper here. Now, how can you imagine the paramagnetic phase which emerges? And so one way of thinking about it, and these are now, I should emphasize, only cartoon pictures, but very useful ones, is that this paramagnetic phase can be understood as a collection of singlets. Now, the way to read such a picture would be that here you have pairs of spins which form a singlet bond, like written here, and then we just put a product of these singlets on this lattice. So this is apparently one possible paramagnetic configuration. And if you now imagine, so this is actually good for, this is not bad for the Heisenberg exchange, because there are still nice singlet bonds here where you get -3/4 of J as an energy. But if you now imagine acting with this ring exchange term onto, let's say, this square, then you can get a flip like this, because this is what this ring exchange does. And you can do this at various places here on this lattice, let's say here and here. And this tells you that the true ground state might be a superposition of many of these configurations. So this is certainly one possibility. And then one could consider essentially equal weight superposition of all of these possible dimer coverings or singlet coverings of the square lattice. And this is actually what was first discussed by Anderson for the triangular lattice Heisenberg model, which has been termed the resonating valence bond state. So this is one candidate wave function. And again, an equal weight superposition of all possible singlet coverings. This is a state which doesn't break any symmetries. So it's a singlet apparently, and it doesn't break lattice symmetries. But an alternative state to look at would be a so-called valence bond solid, where this here is a dominant configuration of the ground state wave function. But this is now an ordered state of singlets. You could also call this a singlet crystal, where which actually breaks now rotation and translation symmetry of the lattice, because your translation symmetry is broken because you have here these favored arrangement of these singlet bonds. It's interesting to discuss the elementary excitations. I will be finished in 1 minute. Do I have another minute?
Yeah, we've asked you a lot of questions, so please.
Okay, so means I have 2. So it's interesting to discuss the elementary excitations of these states. So let me start with this RVB liquid. So again, liquid I call this because it's a state which only has short range order, so no symmetry. And spin excitation apparently can be discussed if I now break up such a singlet. And the pictorial way of doing this would be to draw this triplet state instead of the singlet. And then I can ask the question, what if I consider these two arrows here as independent spin 1/2 objects? So I can try to start moving them apart. And if I do this, I apparently have to rearrange those singlets in between. And I can do this further. And if I do this further, then apparently I conclude that I can always do this. And I don't have to pay a large amount of energy because this state was a liquid anyway. So in other words, there was no preferred configuration for these singlets to begin with. In other words, I can happily move out these objects to plus and minus infinity, and probably I only pay a finite amount of energy for that. Which means that the true elementary excitation is this object and this object alone, and not a bound state of the two. Which means this is a case of fractionalization, where this triplet spin 1 excitation, which I started with, now fractionalizes into two spin 1/2 excitations, which carry spin 1/2 but no charge, and this is what we would typically call a spin-on. This is very different if I do this in the valence bond solid. So again, the same type of cartoon. I start with this state. Now I try to separate these two objects, and what I have to do is I have to rearrange dimers in between, and apparently now I have to use configurations where I deviate from this original preferred configuration, the valence bond solid one. And since the statement to begin with was that the system prefers this solid configuration, the regular arrangement of dimers, I presumably have to pay an energy here for each misplaced dimer. And then it means that I have to pay an energy which is linear in the separation between the two objects, which means I cannot move them out to infinity without paying an infinite amount of energy, which means here I don't have fractionalization, but instead I have confinement by this linear confinement potential. Okay. And I would have still a few slides on the theoretical description of these phenomena in terms of gauge theories, but I guess I can postpone this until tomorrow, day after tomorrow. Thank you.
Thank you very much. Question in the back.
So you showed two cases. One is already liquid. So there you can expect a first order phase transitions. And here you are showing a valence bond solid which has some kind of symmetry. You can expect a second order phase transitions here. Am I right? Or?
Are you referring to the transition from such a state to the metal? Or
yeah, like any kind of transitions when it happens.
This discussion here on level of these cartoon papers was a discussion in the spin-only model. So, but of course I can go back to phase diagrams like this. So you were asking about this type of transition here. Is that right?
Yeah, this is the spin liquid which is first order.
Or let's say, let's even go back to the other ones. For instance, these guys here. Yeah, here are two. So here there is the valence bond solid, presumably. Here there is a spin liquid, again, presumably. Experimental evidence for these two, the experimental support is non-zero but not 100%. So should be careful. Why are you saying that this should be first order and the other one second order?
That should be second order. There should be a point on critical point because you are breaking a symmetry, then you are restoring the symmetry back on the other side. Right?
So, what we could discuss is, of course, the question whether, suppose we have this valence bond solid here. We could discuss the question whether this metal insulator transition, which is supposed to occur from here to here, occurs at the same point where the lattice symmetry is broken. So, is that the type of discussion you are heading for? Because
kind of, that has to be at zero temperature, right? That transitions.
Yep.
Well, this one doesn't have to be, right? It's a first order.
So experimentally, this position is first order. Note also that here the superconducting phase intervenes, which so far I have not discussed. So we could, in theory, we could eliminate the superconductor and discuss whether this transition between the metal and the valence bond solid is presumably first order or second order. And I'm not sure whether I have a good answer for this. So one could, of course, say there are two things going on: metal to insulator, and let's say no symmetry breaking to a valence bond solid, which breaks symmetries. And if you believe in Landau theory, then these two things, if they happen together, they should happen together in a first order transition. Or there should be two separate transitions.
I'm referring to Sasdev's theory, quantum theory.
there are tons of models and theories for those transitions which have been discussed. I don't want to single out anyone at this point. I have to emphasize that there is no reason to believe in concepts of Landau theory for transitions of this type. So it's true that Landau theory would tell you that if there are two different transitions going on, that if they occur together, it should be first order unless there is fine-tuning. But we have now various examples which go with the name of deconfined quantum criticality in models which we understand better, where actually those Landau paradigms can be violated. And I could well imagine that those Landau paradigms are violated here as well. So in other words, at this point, based on theory, I cannot make a firm statement. Experimentally, this transition is first order, and again, about this one, I don't recall what the experimental statement is. But on theory, I guess there was room for second order transitions for all the Mott insulators I described. And I guess there's just relatively limited experimental data because not many systems have been considered where those things potentially occur.
From that phase diagram, does that mean when pressure increases, the U energy decreases?
That's a good question. The main effect is actually that you change the kinetic energy, because these are very soft materials. These are organic crystals, and so the main effect of pressure is that you increase the overlap between the molecular states. So you increase the kinetic energy. The U is an intramolecular property that approximately stays constant. But so the ratio of T over U, so kinetic energy over interaction, is changed by increasing T. So the hopping term.
You are privileging the two-dimensional case. What about 3D?
The V203 is 3D, right?
Yeah. And the full height also.
I'm sorry about that. I'm sorry. I'm not doing this. I'm not doing this on purpose. So the examples which have been investigated to some detail turns out to be that they are two-dimensional. One reason, in particular here, one reason is that it's easier to get rid of magnetism in lower dimensions. In 3D, the Mott insulator is more likely to be an antiferromagnet than in 2D.
I'll show you that when you have a non-bipartite case, you have less. Of
course, we know of let's say spin liquids also in 3D. There is spin ice, and there's pyrochlores, and there are various materials. For most of the interesting 3D insulators, which are not simply antiferromagnetically ordered, I'm not aware of a possibility to tune them into a metallic phase and half them. I guess this has not been achieved because you need to have a relatively small U. I don't think. I'm not aware of it.
That's the case of the two.
So there is apparently one example, but.
On the slide where you have the iteration procedure for DMFT,
Yes.
should one of the G's be green, or is it the blue G at both top and bottom?
Sorry, your question is.
Sorry, at the top and the bottom, are they both blue, or should one of them be green?
I didn't explain the colors. So that actually refers to the previous slide. I guess the colors are correct on this slide. Let me see. So the G is the local Green's function of the impurity model. This blue G, and the curly green G is the Green's function of the environment which describes the bath of the impurity model. And so this is the distinction. And I guess this is the procedure how you get this environment Green's function from this local Green's function. This is a K summation or an energy summation depending on how you view it. And this generates the local Green's function from the lattice model. And this is the way how you calculate the effective environment for the impurity. So I guess the coloring is correct.
So I have actually two questions about this. When you say the correct phase diagram, is that correct?
Correct phase diagram?
Or after this you have the slide which is correct.
This is a phase diagram, yes.
No, I mean afterwards.
Afterwards.
You mean the red one, with the yellow. See if
You're asking whether this has been calculated,
yeah, I mean that.
or whether this is just a cartoon picture for physics today.
Yeah.
It's taken from there. And this is a cartoon, but I believe, so I mean what you can do is you can of course put in long-range magnetic order, fluctuationless long-range magnetic order in DMFT. So this is possible. So in other words, the phase diagram I was showing before without this ordered phase was actually where you suppress symmetry breaks by hand, so to say. You only consider paramagnetic phases by construction, because you assume the equations, the solutions to be spin symmetric. If you don't do this, then you get fluctuationless static magnetism into the game. And if you do this on a frustrated lattice, I believe you can construct something like this. So there are papers in the literature where people consider, for instance, the beta lattice with next neighbor hopping and also field lattices. And I guess they have constructed something like this. But this is a cartoon picture, and I don't really know how the real result looks like. But I recall that there were papers which actually reported the presence of an ordered phase and this line sticking out. So this is a result which is based on real calculations, as far as I recall.
But can I ask the same question in a different way? So you can also, there's the word generic there. And
I put this there, perhaps
so DMFT is exact in infinite dimensions, which is a very special case, right? So why
You notice that I did not advertise this. So you're asking why do I call this generic?
Yeah.
That is a justified question, and perhaps this is too bold. I think this is generic in the sense, or this could be generic in the sense that of course generic only applies to the part at elevated temperatures. And in the sense that if you imagine a Hubbard model, then if you cool down, then the dominant correlation physics down to a certain temperature will be low. Of course this is an assumption, but I guess it's a very reasonable assumption. And if you say this, then you could assume that, that upon cooling down, the high temperature physics down to some temperature will be described by DMFT. In this sense, I call this generic. And of course, this is also partially, I've partially written this because the high temperature part seems to agree with experiments. I mean, that is of course ultimately what we have to use as a gauge. And the low temperature physics is clearly non-generic. And I guess I got this message across.
Okay, there are, I think, more questions, but I also sense a certain restlessness maybe caused by smelling of or anticipating langoustine and soup de poisson and various other wonderful things which await us all in the village. So let's first thank Matthias again for